Okay, so I guess I can begin. I'll begin. Hi, everybody. I'm Peter. That's me. I am from SoundCloud, and I'm going to be talking to you today in a rather short 25-minute talk about search and discovery at SoundCloud. So this is going to be kind of like a like a use case presentation. What does that mean? So here's the outline. First, I'm going to talk a bit about our search product, how it evolved from the early days to where it is today. I'm going to talk about the components of that search product, including specifically how we do relevance ranking. And at the end, I'm going to talk a bit about our service-oriented architecture and why I think it's good. Okay, so starting, the evolution of search. How many of you guys work in companies like a small startup that ships a product? That's pretty vague. Anybody hands, like shipping a product? So at SoundCloud, we started with, like many other startups, we had a product vision, and the product started as what's known as a monorail app. So this means it was written in Ruby on Rails, and it's kind of shipped as a blob to a bunch of servers, and that's how we serve our product to the web. And when you build a monorail app, it kind of, I guess, looks like this. So here's your monorail app, and it's just kind of like one process, and everything's fine, right? And it's actually not a bad way of building a product, because you can iterate really quickly on features, and there's not a lot of resistance. You don't have to think about a lot of things. So this is cool. We had a product for a long time, and one day we decided we needed a search feature, as you do. So how does that look when you need to add a new feature to a monorail app? It kind of just goes like this, right? So you just stick a search controller on the side, and there you go, you have it. Cool. Day one, roll out a search feature pretty quickly, works pretty well. So over time, you start connecting some things to search, you wire up some features, and it kind of works okay, right? Like, there's not a lot of complexity there. But as time goes on, things start happening, right? For us, at least, search was backed by a solar infrastructure. And what ended up happening was after a few features, after a few bug fixes, we found that we were getting a lot of coupling. So we would get solar grammar directly in our app code. We would directly mutate master engine state in places where it shouldn't be. And I think if you work for a small company, or indeed any company that ships a product, this is kind of like a common refrain, like things got to get done, so this is kind of what happens. So depending on your ability to deal with that, this can be easier or harder. But for us, after a while, it got really bad. We lost our ability to iterate quickly. We lost our ability to roll out new features. And critically, we lost our ability to maintain our infrastructure. So when something bad happens, we couldn't jump in and fix it efficiently. So when this continues for a long time, of course, you end up basically with this, right? We call it a big ball of mud, right? So like everything's just kind of stuck together. And yeah, nobody wants to work in an environment like this. Although I can imagine, does this look familiar to anybody? Any software? Yeah, right. Things kind of inevitably end this way. So we juggled these issues for about a year, actually. And finally, we decided enough. We need like a proper first-class search part of our product. And we asked ourselves, how are we going to do that? So how do we fix this problem? We did a survey, and basically, we landed on ElasticSearch. We decided we were going to do greenfield development, so build this new search product up from scratch, which was pretty nice. We were going to do a parallel dark launch, so build it in parallel and then put it out there, use internally for a while, roll traffic over. Migrate traffic slowly, and then as the need arose, we were going to scale it out horizontally and vertically. So that was kind of the plan. The question is, why did we choose ElasticSearch? A lot of reasons, actually. First and foremost was that there was a good API. It was coherent, it was reasonably documented, and this actually goes for a lot, right? If you ever download a piece of software and within a few minutes you're able to like boot up a little mini cluster, in this case, on your laptop, and you can like play around with it, and it's behaving like you expect it to, this is like giving you confidence, right? And ElasticSearch gave us confidence in this way. It provided a clear path for growth, and by that I mean both horizontally in terms of scale and vertically in terms of high availability. A lot of products on the market, I guess, in the search space claim this, but we saw that Elasticsearch kind of had it, so this was really nice for us. Elasticsearch came with a lot of batteries included. By that I mean features that we knew we wanted and features that we already had and had to implement. So things like faceting or stuff like this. It's all there. Cool. And kind of last but not least, Elasticsearch is working like we kind of expected it would. So there's this concept of principle of least surprise where, like, if you walk into a room and you hit a light switch, you don't expect the garbage disposer to turn on, right? You expect the lights to turn on. Has anybody worked with a piece of software that violates the principle of least surprise before? It's like a really terrible thing, right? Like, you lose all your confidence in your ability to develop it and maintain it. You just start fighting it, and when that happens, your productivity goes into the floor, and it's just not a good experience for anybody. But Elasticsearch is nice that it doesn't have this property. When I submit something to the JSON interface, for example, it kind of does what I intuitively expect it should. That's for indexing, that's for searching, that's kind of for everything. So this is cool, and it's also basically true for failure modes, which is a big deal. When the cluster dies in a particular way, Elasticsearch does what you expect it ought to do in that situation. So this is why Elasticsearch. So now I want to talk a bit about our components as we built them, and of course maybe the most important would be our relevance ranking. So how many people are familiar with PageRank from, I guess, Google way back in the day? Okay, about half. So very quickly, this is kind of how PageRank works. You can imagine the internet is these 4 pages. There are incoming links to C and no incoming links to A, and from that you can kind of deduce that C is a more important page than A. This is all represented in a matrix, and then you run some calculations, and at the end of the day, C gets a higher page rank than any of the other pages. Okay, this is fine, this is cool. You have pages, and you have a single type of incoming edge, which is like a hyperlink. But we can extend this model, and indeed we did in the SoundCloud universe, but it's a little bit too simple. We have here only pages and incoming links. In SoundCloud, we have different business domain objects and different kind of edges in our social graph. It's not really a social graph. But that kind of looks like this, and we call it disco rank for discovery rank. So you can imagine this is meant to be a person. This, I think, is a set. I don't know what that is. He's made that. Anyway, so, okay. A person creates a sound. A sound can be part of a set. A person can create a set and favorite a sound. You can imagine like all the things you can do in any sort of rich business domain landscape. So we model all that in our social graph, and we apply the same sort of PageRank rules to it. And from that, you can derive a disco rank for all of the entities in that graph. And they can be treated in aggregate, so it's like a universal disco rank, or they can be treated individually. And from that, you can deduce a kind of importance or relevance score for each of the entities. Okay, so what does that give you? We do all these calculations offline because it's pretty heavy. I think it takes, not sure how long. A delta is like maybe half an hour or something like this, and to do it from scratch, it's several hours. We serialize the output of that, so we serialize that big matrix with all the values into a compact array, and it's loaded into Elasticsearch in what's known as a custom scorer module. So we actually load it into the Elasticsearch instance in memory. This is another one of those like batteries included things that's really nice. That was good for us to extend. Then when at query time, we do kind of like a hybrid two-phase thing. So a two-phase query is you go to Elasticsearch, you get all the documents back, and then as a totally separate step, you would like re-rank them from another data source. We're able to do this entirely within the Elasticsearch query, but internally it's doing its TF-IDF lookup, and it's getting all the matching documents on a text basis, and then it's applying this ranking internally. So that's kind of why it's hybrid. So that's how it works at query time, and then in order to keep it fresh, we recalculate and reload this serialized array every, I don't know, couple hours, something like this. And that's okay. Things aren't changing that rapidly. So that's what disco rank is in like the base form, but it turns out you can use this type of relevance ranking to do other product features, which is pretty neat. For example, If you add a time component to the edges, you can kind of weight things according to how recent they happened, and from that you can derive kind of like a hotness score. So if a lot of people favorite a track all at once, then that becomes more relevant, and then over time, if no one else favorites it, it becomes less relevant. So that's how we do hotness in some areas of the product. Similarly, you can combine the rankings of user entities with some other elements of their behavior from other parts of the site, and from that derive a trust score. So how spammy a user is, for example. Very spammy users will have a lot of outbound edges and perhaps no inbound edges, something like this. So DiscoRank is like kind of a platform to do a lot of other really neat things on the product. Okay, so that's like one component of the search infrastructure, but there are other ones. What's the bigger picture? You can probably wire up a search component into your product in a lot of ways, but in the base case, it probably is going to look like this, right? You're going to have your cluster, and for us, it's a separate piece of infrastructure because we already had the master authoritative source of all of our records. We're going to index events into it, index records into it, and then later on query out of it. So the question is, first of all, how do you index into it? Okay, so here's kind of what our indexing infrastructure looks like. We have, luckily, this RabbitMQ message broker. So everything that happens on the site when you upload a track, when you like somebody, when you change your user details, things like this, a message is materialized onto the broker. We listen for the things which are relevant to the search infrastructure, and when we hear them, we send a signal to this little red box here, which is the search indexer. It's converting that signal into a materialized view, which is all the stuff that we care about searching. So signal, materialized view, and then we use the ElasticSearch API to index into the cluster. So this is pretty fast, actually. From the time you click save on your user record to the time it becomes searchable on the other end of that cloud is usually around 2 or 3 seconds, and pretty good. So that little red box is our indexing application. It is a single-purpose application, which is stateless and idempotent. Originally, it was written in a very naive way, in the Go language, if that's relevant to anybody. And then over time, we've iterated to get it to the point where we're doing sub-microsecond per document index times. So that's kind of the development philosophy. From that, we can do an entire catalog in about, last I checked, it was like 45 minutes or something like this. So that's all of SoundCloud into Elasticsearch in about 45 minutes. Cool. Okay, so there's indexing right side. On the other side is read. Unfortunately, this diagram isn't very interesting. There's just a box there. So this is how we search. You can imagine that this is basically just a query grammar translator, like a DSL translator. It's going from the ElasticSearch domain up here, so like record, field, this sort of thing. And on the other side is the SoundCloud grammar, so like created in the last month, BPM, whatever. It's very simple, very declarative. Again, single-purpose application, stateless and idempotent. It just does this DSL translation, and it's built around a Elasticsearch library, which we wrote for this purpose, and which is open source. Okay, so there's kind of the big picture of the basic search pipeline. There are some other products that are built on top of Elasticsearch. For example, we have this Explore tab. If you go to SoundCloud, there's an Explore tab up there. That is also in the back end, a single-purpose application, which is stateless and idempotent. I put stateless in quotes because what it does is, on a regular interval, make kind of complex queries into our Elasticsearch cluster, which are keyed in or predefined for each of the things we want to expose. And though the results of those queries are cached, so we can serve very quickly these kind of cached buckets of content, and we can refresh them about every 5 or 10 minutes or something like this, and this is totally fine, right? Things aren't changing really that rapidly. And from that, serve very quickly results. So again, we're talking nanoseconds or microseconds to get stuff out of this. So that's our kind of basic search infrastructure. And maybe one thing you noticed about all these things are these first 2 lines were basically the same on all of them. And it turns out that's on purpose, and it's a really good thing, because we have what I call a service-oriented architecture. I guess for a lot of people, this means different things. You ask 10 developers, you get like 10 different responses. But at SoundCloud, this is what I mean by service-oriented architecture. We have our own internal platform. It's called Bazooka, and you can envision it like kind of internal Heroku or something like this. It follows these semantics where you're committing and pushing to a remote repository. That is your build step. And then after that, you have the ability to scale that revision of your service up into however many instances you want. We treat our API layer as sort of a firewall. So the Bazooka platform, the Bazooka orchestration service is kind of a free-for-all. And if we want to allow authenticated connections in or something like this, allow internet traffic in, we always route it through this API layer. That makes things a lot easier for us. And everything which is deployed on Bazooka, everything in our service-oriented architecture abides these 12-factor rules. Has anybody heard of 12-factor, or is this like totally new? 12-factor, anybody? Okay, so this is really cool. And if you're not doing this, you should be. Okay, this is my evangelism part. Let me talk a little bit about what a 12-factor app is. There are indeed 12 factors. I will only talk about 5 of them because I'm pushed for time, I guess. So you should write software this way. Your application, your 12-factor app, should come from a single code base, which usually means repository. If your application comes from multiple repositories, then it is indeed separate applications or some kind of communicating network of applications, okay? So that's like the concept of application. You should store your config in your environment. This means not shipping configuration files along with your application. It allows you to very easily have separate environments, staging, development, production, and it allows you to transition very cleanly between them. You should treat backing services as resources. So this is critical, especially in distributed environments. You can't kind of abstract the network away. I'll get more into that in a little bit later, but the point is if you have a MySQL database, if you have another service that you're talking to, these things, you need to understand them in terms of, in the context of they can fail, right? That connection can die, and you need to deal with that as a first-order thing. You can't ignore that. Every 12-factor app is stateless, kind of stateless. That means when you start it up, it should start up very quickly. It shouldn't rely on having a certain amount of neighbors that it can communicate with. You should be able to start as many instances of these things as you want, and your overall application, your overall system should function the same way, basically. And 12-factor applications achieve horizontal scaling, so scaling for load, with a process model rather than with, let's say, a thread model or anything else like that. That said, your processes should still be concurrent. You probably shouldn't be locked into a single-threaded sort of event loop. You can do this, but if you're following Heroku at all, you notice they got into some trouble a couple months ago because their routing infrastructure didn't take into account that many applications aren't concurrent. They aren't C10K compatible. So to avoid that class of problem altogether, it's better to be concurrent. Okay, so these are some things about 12-factor apps. If you're interested at all, please go to 12factor.net. It's really good stuff. That's all I'll say about that. Okay, but why do we do this, right? If we had this monorail app back in the day, why are we transitioning to this sort of service-oriented architecture approach? Probably the biggest reason is simply velocity. If every application is written in this way, it's kind of always serving like a single business use case, a single set of rules that are usually very tightly related. So if every application you write is like this independent thing, which is having a single purpose, then there's very little you have to like learn when you're coming into this code base and like maybe you want to maintain it or refactor it. You don't have to consider a lot of different things. You only have to consider the core problem that it's solving, which is like very obvious and like simple when you hear it, but it goes a really long way. If there's less to learn and to change when you have to do this stuff, you can basically work as if you're always refactoring. So every time you need to change a service or an application because of a new business rule or because of a new constraint or something like that, you can and indeed should say, well, is it better if I just rewrite this from scratch? And the cost of doing that, if you're writing these service-oriented architecture services, is very low. For example, the indexer I rewrote from scratch probably like 5 times before it got to where it is in the course of 5 months. And I guess at a lot of companies, you can't achieve that kind of, your services are too big to achieve that kind of iteration loop. So SOA gives you velocity in that way. And velocity, of course, gives you developer happiness, which really can't be understated. I don't know about you, but if I am happy, I am way more productive, like order of magnitude more productive. If I can like understand what it is my services are doing without having to guess about like that black box or this thing that I didn't write that's been there for 2 years, I can do a lot more, and the company gets a lot more value out of my salary. So this is really cool. Another component of happiness is that all of my services abide like contracts, right? So they have to only satisfy these business rules, and it's totally up to me how they do that. So we're at SoundCloud totally polyglot. We have people writing apps in Clojure, Haskell, Go, Ruby, a lot more languages that I can't bring to mind. And this is fine, right? As long as they satisfy their contracts, totally cool. That's also good for developer happiness. And also important on a technical level is that distributed systems are complex. And you truly cannot just say, well, the network is just like a function call, and if it fails, this means your system will crash in a way that you can't recover from. You have to think about the network as a first-order thing whenever you go from one computer to more than one. And when you think in terms of service-oriented architecture, this sort of thinking happens naturally. And this is really important for writing reliable software systems. Okay, there's my SOA evangelism. So, at SoundCloud, ElasticSearch core, SOA infrastructure, that is our search and discovery experience. And I am done. Thank you very much.